Hello, my name is Arno Smets. I am a professor in Photovoltaic Materials and Devices group at TU Delft. Welcome to the first course in our MicroMasters series, Solar Energy Engineering. This first course is called Photovoltaic Energy Conversion. I will introduce you to the first course in a series of courses that complete our MicroMasters for Solar Energy with a focus on photovoltaics. Photovoltaics refers to a field that deals with the conversion of solar energy directly into electricity. This video serves as an overview of the course to let you know what to expect in the coming weeks as you become an expert on the physics and engineering of photovoltaic energy conversion. In this course you will learn all of the fundamental physics behind photovoltaic energy conversion. Let me first introduce the lecturers for this course. I have already introduced myself, Professor Arno Smets, and I will be accompanied by Professor Miro Zeeman and Associate Professor René van Zwaay. All three lecturers are professors at the Delft University of Technology and work in the Photovoltaic Materials and Devices group. Our group has expertise in teaching and research in all aspects of photovoltaics, from fundamentals to device fabrication and full system design. The course Photovoltaic Energy Conversion is split into 4 parts. The first week serves as an introduction to the field of photovoltaics that deals with the conversion of light directly into electricity. The course then really starts with semiconductor physics. The reason why we shall spend significant time on the topic of semiconductor physics is that the actual energy conversion takes place in semiconductor materials. Understanding the relevant physical properties of semiconductors is of utmost importance to any photovoltaic engineer. This part will span 4 weeks and will be the most challenging part of the course from a physics perspective. Then we will spend 2 weeks on light management. This part of the course will focus on optics concepts and light trapping strategies in order to maximize light absorption in a solar cell. The final section of this course serves as a wrap-up. We will look at all concepts given in the course so far and find out how they result in electrical losses. This last week will give you the tools needed as a photovoltaic expert to properly design and engineer solar cells. Let's go through all these 4 sections in a bit more detail. In our introduction we will tackle 3 main topics: energy in general, energy provided by the sun and the solar cell. By the end of this introductory week you will be able to explain what energy really means from a physics perspective and how we can convert incoming energy from the sun into useful electrical energy using solar cells. In the introduction we will first take a look at the sun and the spectrum of solar radiation. What are its properties? What kind of energy does it provide? This is our fuel source and we as photovoltaic engineers must understand it as best we can before designing devices and PV systems to harness its vast energy. We will then look at the very basic concepts of a solar cell. Why can a solar cell convert light into electricity? What are the basic processes that are responsible for this effect? How is a solar cell built up? You will get a taste of this in the introduction week, but get ready to dive deeper into the physics afterwards. Since solar cells are based on semiconductor materials, the next 4 weeks will focus on semiconductor physics. We will answer questions regarding atomic structure of a semiconductor material and the existence of mobile charge carriers, electrons and holes in it and how their concentration can be manipulated by doping. It is important to know the concentration of electrons and holes in a solar cell because they are the carriers of electricity. You will then learn how these charge carriers move around in a solar cell and how extra charge carriers are generated or annihilated in a semiconductor. It is necessary to know these processes in the solar cell in order to properly understand how a solar cell produces electricity. Based on the physics of semiconductors, you will learn about the fundamental performance limitations of solar cells. This will be the most challenging part of the course if you do not have a background in electrical engineering or physics. However, if you stick through this section, you will develop a deep understanding on the fundamentals of photovoltaics. After semiconductor physics, we will move to light management of a solar cell. In addition to the semiconductor physics necessary to understand solar cell operation, you also need to understand how the energy of solar radiation is best utilized in a solar cell. The most basic idea of light management is how to capture the most light with the least amount of material in a solar cell. More light means more energy, and less material means lower costs. We will start with the fundamental optics concepts necessary to understand how to trap light. Then we will explore some strategies that are employed by solar cell designers to trap light in the absorber layer of a solar cell. The final week of photovoltaic energy conversion is devoted to electrical losses in a solar cell. By this point in the course, you will be familiar with how the solar cell works and how to get most of the light into a solar cell and excite electrons in it. Now it's necessary to understand how to deal with the photo-generated electrons. Here we explain what aspects of a solar cell can reduce its electrical performance in terms of voltage and current that the solar cell can deliver. Finally, we will explore some engineering tricks that can be used to reduce these losses. We strongly recommend following along in this course with our textbook, Solar Energy, Physics and Engineering of Photovoltaic Conversion Technologies and Systems. This textbook is available as a free e-book for any e-reader on Amazon. Hard copies are also available for purchase at Amazon.com as well as other retailers. Now the assessment. Following most of the video lectures, you will find exercises to apply your new gained knowledge. These exercises are meant to test and improve your understanding of the concepts discussed in the videos. So try the exercises and don't be afraid to make a mistake. All the weekly exercises combined count for 15% toward your final grade. The practice exam counts towards 5% of your final grade and is meant for students to practice and get familiar with the format of the proctored exam. The proctored exam is only available to ID verified students and counts for 80% towards your final grade. You can qualify for the PV1x verified certificate by achieving a minimum final score of 65%. Besides the regular content, PV1x also features a live webinar in which you can interact live with the course team. The webinar generally includes a behind-the-scene tour at the Delft University of Technology, an interview with a titan of industry, and an interactive discussion in which the course team treats the issues introduced by the students. Look for more information in the webinar tab of the Getting Started week. The students will have access to the exciting challenges. The challenges are topical issues where the course team interacts with the students. Each challenge will receive a feedback video. All the information provided in this video can be found in the course syllabus. On behalf of the entire Photovoltaic Materials and Devices team here at Delft University of Technology, I'm very excited to provide this course for you. I hope you're ready to jump right in and become an expert on the physics and engineering of photovoltaic energy conversion.